Good evening, students. So today, let me take up the formulas and the concepts of dual nature of radiation and matter. This is quite simple chapter, which is going to be a scoring one in competitive level. Easily you can analyze the concepts, but the concept should be as strong for you. Now, in this chapter, we are going to talk about the emission of electron. Emission of electron, that is what we called as an electron emission. So what is electron emission? Suppose if you are going to consider a metal, you know that the metal consists of a free electrons. The metal consists of a free electrons which are there in the metal. These free electrons can be taken out from the metal. We can remove that electron from the metal. This phenomenon is what we call as the electron emission, isn't it? So electron emission means the removal of electron from the metal surface. Now, we can remove the electron which are there in the metal by different methods. By the different methods, we can remove that. The first method is you have to heat the metal. By giving the heat energy to the metal, we can get the electron out from the metal surface. That phenomenon we call it as a thermionic emission. So what is thermionic emission? In the thermionic emission, we are going to take out the electron from the metal surface by giving the heat energy. That is what we considered as a thermionic emission. The second one, by giving the radiation. By giving the radiation, you can take the electron. That phenomenon or that emission, we call it as photoelectric emission. Photoelectric emission. So what is photoelectric emission? It is the emission of electron from the metal surface by giving the heat energy, the radiation, not heat energy, radiation. By giving the radiation, we can take out the electron from the metal surface. That is what we called as the photoelectric emission. You know what is the radiation consist of? This radiation consists of a energy in the form of a packets. We call it as a photon. That energy is given by the formula E is equal to h nu. What is nu called? Nu is a constant called the frequency, which is also equal to hc by lambda. So please remember this formula where h is equal to what? Planck's constant. Here h is called as what? The Planck's constant. What about nu? Nu is a constant called what? The frequency. C represents what? The speed of light. The speed of light. And lambda represents what? The wavelength. Lambda represents the wavelength. H is Planck's constant. Nu is the frequency. C represents the speed of light. Lambda represents the wavelength. What is the value of the Planck's constant? Value of the Planck's constant is 6.625 into 10 raised to minus 34 joule second. Frequency varies from radiation to radiation. You know the speed of light value is 3 into 10 raised to 8 meter per second. Wavelength also varies from radiation to radiation. Now, looking this formula, E is equal to hc by lambda. This is the energy associated with the wavelength. So if you know the wavelength, how to calculate the energy upon? Energy is given by the formula E is equal to hc divided by lambda. hc divided by lambda. But please remember, for competitive level, instead of using this hc by lambda, you simplify after substituting h, c values and all those things. Please remember this formula 12400. 12400. 12400 divided by lambda. Please remember, this lambda should be in angstrom. Lambda should be in angstrom. Please remember this. And you will get this in electron volt. You won't get it in joule. You will get it in electron volt. So what is the shortcut formula for the energy? You can use 12400 divided by lambda. But please careful, this lambda should be substituted in angstrom. Lambda should be substituted in angstrom. So whatever the value you are going to get, that must be in terms of what? Electron volt. Isn't it? Clear? So because you know the value of H and C, no. After knowing the value of H and C by substituting there, if you simplify, you will get that particular format. 12400 divided by lambda. But be careful, lambda must be substituted in angstrom. Don't substitute it in nanometer. You have to substitute that lambda in angstrom only. Then whatever the value you are going to get, that should be in electron volt. So this is the energy formula for a given radiation. Please remember. So how to take the electron from the metal surface means either by thermionic emission or by photoelectric emission. In the thermionic, we are sending the heat. In the photoelectric emission, we are sending the energy. What is the energy radiation? It is going to be either measured in terms of frequency or in terms of wavelength. In terms of frequency, it is given by h into nu. In terms of wavelength, it is given by hc by lambda. And lambda should be substituted in angstrom. Then whatever the energy we are going to get, that energy is going to be in terms of electron volt. Please remember that. Clear? Yes. Now, after analyzing the energy, so what is the energy formula you have studied? It is hc by lambda actually, but for competitive level, instead of using this, we are using direct formula, that is 12400 divided by lambda. This lambda should be substituted in angstrom. Remember that. Yeah. Now, let me know the another important parameter, that is work function. Work function phi. What is that work function phi? For example, if I considered a metal, this metal consists of what? Electron in the outermost orbit. Now, to remove this electron from the metal, I should give some radiation, right? Yes or no? I should give the radiation to that metal. If I give the radiation to this metal, this electron is going to absorb this energy. This electron is going to absorb that energy. After absorbing that energy, this electron will come out. This electron will utilizes a certain minimum energy here. By using that minimum energy, the electron is just coming out. That that minimum energy only we call it as a work function. So what is work function? What is work function? The minimum energy it is going to use. The minimum energy required for the electron to just come out from the metal surface. What is that minimum energy called? Work function. That is denoted with the formula H into nu naught. Since energy is minimum, this frequency should be minimum. Or we can also write it as Hc by lambda naught. But lambda naught should be maximum because this work function and wavelength are inversely right. To get the work function minimum, threshold wavelength should be maximum. Threshold wavelength must be maximum. So whatever the work function we are using, in that work function, the threshold frequency must be minimum, but the wavelength should be maximum. This frequency, which is minimum, but this wavelength is maximum. Remember, this minimum frequency is what we called as the threshold frequency. What is this called? Threshold frequency. So what is threshold frequency? Threshold frequency is the one. Threshold frequency is the one where it is a minimum frequency. For that, the electron is just going to come out from the metal surface. Similarly, whatever the maximum wavelength we have, that maximum wavelength, by using that, we are taking the electron. That maximum wavelength for which electron is coming out is what we called as the threshold wavelength. It is called as what? Threshold wavelength. Please remember, threshold wavelength is the maximum wavelength for which the photoelectric effect takes place. And threshold frequency is the minimum frequency required for the emission of electron. Suppose if you give the frequency, less than the threshold frequency, if the frequency is less than the threshold frequency, for this case, there will be no emission of electron. For this case, there will be no emission of electron. If the frequency is less than the threshold frequency, there will be no emission of electrons. Clear? So please remember these two particular formulas. And the basic important properties you have to remember here. What are those particular properties? Now, one by one I will write. For the emission of the electron, what is the first basic condition? The frequency, whatever the frequency you are going to incident, that should be more than what? Threshold frequency. The incident frequency must be more than the threshold frequency. Incident frequency must be more than the threshold frequency. Second condition, whatever the kinetic energy is there in the electron, because after this electron emission, this electron starts to move towards the anode. Whenever this electron is moving, it will always associated with what energy? Kinetic energy. Please remember, this kinetic energy is directly proportional to the frequency. I mean to say that as the frequency increases, the kinetic energy also increases, provided this frequency must be more than threshold. Suppose if the incident frequency is less than the threshold frequency, there will be no emission of electrons. So kinetic energy is directly proportional to the frequency. The another thing, whatever the photoelectric current is there, that photoelectric current is directly proportional to the intensity. But please remember, This photoelectric current not depend on frequency. Photoelectric current not depend on frequency. Please remember this. Photoelectric current does not depend on frequency. Photoelectric current is directly proportional to intensity. Kinetic energy is directly proportional to frequency. Incident frequency must be more than the threshold frequency. These are the conditions it has to be satisfied for the emission of electron. The next, another very important one, there is some negative potential to stop the electron. That negative potential, we call it as a stopping potential. This stopping potential is directly proportional to the kinetic energy. This stopping potential is directly proportional to the kinetic energy. Please remember this. Stopping potential is directly proportional to the kinetic energy. Now, whatever the explanations we have given here, usually in competitive exams, they may ask in terms of graphs. Suppose if I consider the graph between the kinetic energy versus the frequency. Kinetic energy versus the frequency. What will happen? From origin till certain frequency, there will be no emission of electron. Till certain frequency, there will be no emission of electron. This frequency, we call it as a threshold frequency. This is called as the threshold frequency. As this frequency increases, kinetic energy also increases. As this frequency increases, kinetic energy also increases. So it is going to be a straight line. Please remember, if I find what is the slope of this straight line, you know how to calculate the slope. That is tan theta, right? Opposite by this, adjacent. If you find the slope for this graph, it is going to be the Planck's constant. So what is the slope of kinetic energy versus frequency represents? The Planck's constant h. Second graph. It is between photoelectric current versus the intensity. Photoelectric current versus the intensity. As intensity increases, the photoelectric current also increases, right? So I is directly proportional to intensity. So current is denoted with small I. Don't get confused. So I versus capital I, current versus intensity, is also a straight line. Now, let me plot the graph between the stopping potential versus the frequency. Here also, as the frequency increases, stopping potential also going to be increases. It is going to be a straight line only because it is just kinetic energy divided by electron charge is called that work done is equal to the potential difference into the charge brought. Here the work done is nothing but the kinetic energy. So kinetic energy is nothing but E into potential. So this is kinetic energy E times of potential. This potential is stopping potential Vs. Or what I'm going to write, stopping potential is nothing but whatever kinetic energy we have divided by E. Kinetic energy divided by E represents the stopping potential. So for this case, if you find the slope, here the slope is not going to be only a Planck's constant. For that, you have to divide by E. So slope is given by H by E if you express the stopping potential versus the frequency. Stopping potential versus the frequency. So this is the basic graphs. Now, let me take the effect of intensity. All these graphs are important. Effect of intensity. Now, let us take the photoelectric current along the y-axis and the stopping potential along the x-axis. Stopping potential along the x-axis and the photoelectric current along the y-axis. Now, I'm going to take the different intensities. Let us say this is the first intensity I1. This is the second intensity I2. Clearly, you can tell I2 is more than I1 because for I2 intensity current is more. For I1 current is less. So I2 should be more than 1. This is the origin. So if you start reducing the potential in the negative direction, this current comes to 0. This current comes to 0. This point where the photoelectric current comes to 0, this potential only we call it as a stopping potential, which is a negative potential, no doubt. So for different intensities, please remember, for different intensities, we are not getting the different potential. We are getting a same potential. So for different intensity, the stopping potential is going to be the same. Stopping potential is going to be the same. In the same concept, let me analyze with effect of frequency. Effect of frequency. Let us take this, the stopping potential along the y-axis. We are taking the photoelectric current only. But please remember, we are taking a saturation current. We are taking a saturation current, but here we are instanting with the different frequencies. We are instanting with the different frequencies. Let us say this is nu1, second one is nu2, this is nu3. So here the photoelectric current is not changing, it is remains same. But frequencies is more. Nu3 is more than nu2, nu2 is more than nu1. Now what will happen if I start reducing the potential in the negative direction? This potential will come to 0 here. This frequency will come over here. This frequency will come over here. So all the three frequencies will not come and meet with the same potential. No. For different currents, you are getting same potential. But for different frequencies, you are not getting the same potential. The potentials are different. VS3, VS2, and VS1. So different frequencies, different potentials you are going to obtain. So please remember, VS3, third potential is more than the second potential. Second potential is more than the first potential. So clearly this tells potential is going to affect with the frequency. So if the frequencies are different, stopping potentials are different. But please remember, different intensities, but the stopping potential is same. That is why I told intensity does not depend on the frequency. Photoelectric current does not depend on the frequency. Only the stopping potential and the kinetic energy depends on the frequency. Got it? Yeah. Now this explanation also given by the Einstein to explain this photoelectric effect. What is that Einstein explanation regarding this photoelectric effect? And also for this explanation, Einstein got the Nobel Prize. According to this, Einstein is going to put the explanation of photoelectric effect on the principle of conservation of energy. On the principle of conservation of energy, the Einstein is going to put the explanation. So Einstein explains the concept of photoelectric effect considering the conservation of energy. What is the Einstein explanation is going to talk about? Suppose if I consider a metal. This is very important, Appa. If I consider a metal, if I incident a certain energy to this, which is equal to h nu, their electron will be there, right? What will happen to that electron? This electron will absorb the energy, isn't it? This electron will absorb this energy. After absorbing that energy, what the electron will do? That electron is going to absorb the energy. After absorbing that energy, what that electron is going to do? This electron will utilize certain minimum energy to just come out, right? That is called work function. No, that is h nu naught. But complete energy is not going to be used as work function. Only a part of energy is going to utilize to just come out. What will happen for the remaining? The remaining energy is converted into kinetic. The remaining energy is converted into a kinetic energy. You know that the kinetic energy is given by half mv square. So whatever the total energy we have incident, the total energy should be equal to work function plus kinetic energy, no? Because according to conservation of energy, energy can neither be created nor to be destroyed. So total energy is equal to work function plus kinetic energy. Total energy is nothing but E is equal to h nu and work function is equal to h nu naught plus kinetic energy can be taken as Ke, or kinetic energy is equal to h nu minus h nu naught, or kinetic energy is equal to h into nu minus nu naught, isn't it? So this is the kinetic energy. So this is the equation. This equation tells that clearly you can give the explanation here. If the frequency is less than the threshold, if the frequency is less than the threshold, what will happen? What will happen if the incident frequency is less than the threshold frequency? What will be the kinetic energy? It will be positive or negative at least. If this frequency is less and if this nu naught is more, kinetic energy will be negative, no? But this kinetic energy negative can't be possible. Because kinetic energy formula is given by what? Half mv square. So here m can't be negative, v square can't be negative. V may be negative, but v square can't be negative. So kinetic energy is always positive. Kinetic energy is always positive. But if the frequency is less than the threshold frequency, we will get kinetic energy negative. Because of this reason itself, electron will not emit from the metal surface. Electron will not emit if frequency is less than the threshold frequency. So this is what exactly the Einstein photoelectric equation tells. But let me learn the different forms of photoelectric equation, which is going to be used for your problems. This is the basic equation which I have explained. Now let me learn one by one the different equations. So what is the first equation? First equation is very simple, right? Energy is equal to work function plus kinetic energy. Energy can be taken as h nu. Work function is h nu naught plus kinetic energy. From this, what is kinetic energy? H nu minus h nu naught. Or kinetic energy is equal to, you know that nu is nothing but c by lambda minus h. What is nu naught? C by lambda naught. You know that kinetic energy can also be taken as half times of mv squared, which is equal to hc by lambda minus hc by lambda naught. So what is v squared from this equation? If you take out hc as common, you are going to get 1 by lambda minus 1 by lambda naught. So this will become 2 times of hc divided by m. Divided by m. What is this maximum velocity v? If you don't want this square, you can take out the root. So it is 2 times of hc by m into 1 by lambda minus 1 by lambda naught. So this is the maximum velocity of the photoelectron, which is going to come out from the. So maximum velocity is given by square root of 2 times of hc divided by m into 1 by lambda minus 1 by lambda naught. This is the maximum velocity. So these are the different forms where we can put the Einstein's photoelectric equation. And also remember, kinetic energy is nothing but what? E into Vs. Kinetic energy is nothing but what? E into Vs, where E represents the charge of the electron, Vs represents the stopping potential. So these are the different forms of the Einstein's photoelectric equation. You have to remember this. All these equations we are going to make use of in the problems. Now, another important concept we are going to analyze, that is matter waves. Matter waves. This was explained by the scientist called by the name de Broglie. So it is also called as the de Broglie waves. De Broglie waves. So what are the meaning of that matter waves? Matter means a small particles. Whenever the particles like electron, proton, alpha particle, you know electron means -1 is 0, proton means positive charge means +1 is 0, alpha particle means 2Ha4, and proton means 1H1, like this. Whenever these particles, minute particles, whenever this particle is going to move in a medium, whenever this small particles moves in a medium, it is going to disturb the medium. What is that disturbance called? Waves. These waves only we call it as the matter waves. So always matter waves means these are the waves associated with the moving particles. These are the waves associated with the moving particles like electron, proton, alpha particle, like that. Whatever the wavelength is associated with this wave, that wavelength we call it as a de Broglie wavelength. What is that called? De Broglie wavelength. So what is this de Broglie wavelength? De Broglie wavelength is the one associated with the matter waves. And please remember the different formulas for the de Broglie wavelength. The different formula for de Broglie wavelength is lambda is equal to h divided by mv, where h is the Planck's constant, m is the mass, and v is the velocity. You know what is mass into velocity? What is mass into velocity? Momentum. Mass into velocity is momentum. And this momentum can also be taken as root of 2 times of m into Ek, where Ek represents the kinetic energy. This can also be written in the form of potential, h divided by root of 2m q into v. What is that V called? V is a potential there. Q is the charge. Q is the charge. V is the potential. So what are the different forms of the de Broglie wavelength? You have to remember this. Addition to this, you have to remember the de Broglie wavelength for different particles. Try to remember that. If they have given the particle as an electron, for electron, h is constant, mass is constant, q is constant. So if you substitute all that particular value, and if you finally remember the calculation part and all, if you simplify that, you will get finally 12.27. You will get it as 12.27 divided by root V. And remember, this is in angstrom. So what is that shortcut direct formula for the de Broglie wavelength of electron? Shortcut formula directly for the de Broglie wavelength of electron is 12.27 divided by root V. You have to write it in Armstrong. Suppose if they have given the proton, if they have given the proton, for proton you will get 0.286 divided by root V, and this also will be in Armstrong. So what is the de Broglie wavelength for proton? It is 0.286 divided by root V. This is in terms of Armstrong. Then what is the de Broglie wavelength for deuteron? Deuteron means 1H2. Deuteron 1H2. Deuteron. This plus 1 is 0 is also called positron. For deuteron, for 1H2, please remember, it is 0.202 divided by root V Armstrong. For deuteron, it is 0.202. Finally, it is for alpha particle, 2He4. Alpha particle means 2He4. Please remember, for alpha particle, it is 0.101 divided by root V. All the wavelengths should be expressed in Armstrong. Please remember that. So these are the 4 different shortcut formulas you have to remember for the particles like electron, proton, deuteron, and for alpha particle. Then suppose if you considered a neutron, you know that for neutron there will be no charge because neutron is a neutral charge. So if you remember for the neutrons, these neutrons which depends on temperature, which we call it as a thermal neutrons, thermal neutrons. That wavelength in the thermal neutrons is given by the formula lambda is equal to h divided by root of 3 times of m into kT. Remember, what is the de Broglie wavelength for the thermal neutrons? The de Broglie wavelength for the thermal neutrons is lambda is equal to h divided by root of 3 times m into kT, where m represents the mass. Here K is called the Boltzmann constant. Remember that. What is K called? Here K is called the Boltzmann constant. Remember that. So this is the de Broglie wavelength for the particles which are in motion. Clear? And please don't consider the photons, because photon is going to travel with speed of light and it is electrically neutral. Whatever the photons are there, we cannot discuss the de Broglie wavelength for the photons, because those de Broglie waves will travel with the speed of light. They travel with speed of light and it is electrically neutral. Since it is traveling with the speed of light, the rest mass of the photon is 0. Because of that reason, we are not going to deal about the concept of the photons in the case of matter waves. And actually, here the electron is not a particle nature in this concept. In the case of this matter waves, we are considering the electron as a wave nature. Actually, we have explained the electron as a particle, but in this case, we are explaining this electron is going to behave like a what? The wave. Electron is going to behave like what? Waves here. Because of that reason only it is considered as a wave nature. And this experimentally verified by the scientist called by the name the Davison and Germer. So Davison and Germer proved experimentally Davison and Germer proved experimentally the wave nature of the electrons. Wave nature of the electrons. So please remember all these particular formulas about the two cases. One is for photoelectric effect. The second case is for matter waves. Based on these two only, we are going to deal about the problems in competitive, especially for NEET. But in the case of JEE, actually there are two more concepts which is not there in our NEET syllabus. That is, one is called the X-ray tube. How that electron tube is going to work under X-ray cases. And also there is one another spectrograph. That is what we called as brain bridge mass spectrograph, which is usually used to determine the velocity of the particles. But we don't use all those things here in the case of matter waves. So these are the formulas you have to remember in matter waves. But in the case of NCERT textbook, as per in NCERT textbook, there is one more principle. That principle is what we called as Heisenberg uncertainty principle. But we won't get any problems on this principle. But it is there in the NCERT. That is Heisenberg uncertainty principle. So you know that according to this uncertainty principle, either the position or the momentum can be measured very accurately at the same time. Can't be measured most accurately. Can't be measured more accurately at the same time. At the same time, we cannot measure both position and the momentum very accurately. Please remember that Heisenberg uncertainty principle equation, that is momentum into position, delta P into delta X, or delta X into delta P should be equal to H cross. Or you can use that H cross as H divided by 2 pi. H cross is equal to H divided by 2 pi. So this is what the Heisenberg uncertainty principle tells. So you have to remember all these formulas apart. Based on this, we can solve the numerical problems in the next class. So in the next class, we can take up the problems based on this apart. I hope you understood the concepts of dual nature of radiation and matter. So you study all these things. If you have any doubts, you can discuss that in the next session. So before going to the problems, we can go with synopsis of these formulas. Then we can straight away start up the problems on this. Okay, pa. I'll stop at this case. We'll continue in the next class. Thank you.